Okay, welcome to the fourth episode of the Quxlang Devlog. It's been quite a while since the last episode. The compiler has gotten a lot further along than before. So now the compiler can actually produce binaries and we can execute them. So that's a big change from the last time we had one of these. So for example, I can run this compiler. I'm going to show my little config here. So it takes two arguments. You have the source code, and then you have wherever you want to write the binaries to. There's not really any other options to the compiler at the moment, so we'll just define kind of the binaries that we want inside this quxbuild.yaml file. So it's part of the source code. So if we want to change like the optimization mode, it's going to be in this kind of quxbuild file. Instead of inside like a command line flag or something. So you don't really set flags like O2 or O whatever on your compiler. You just kind of say, here's my source code, and then you just run the compiler and all the optimizations and stuff go in this file. So it's much easier to reproduce the build that way because the flags that you give the compiler don't affect the binaries that are produced. That's only affected by the source code. Now, there will be some compiler flags, like, for example, maybe a limit on the number of threads the compiler will use or something like that. That's not going to affect the binaries that are generated. So there may be some compiler flags, but none of them will affect the binaries. Anything that affects the binaries is going to be in this quxbuild.yaml file that you point the compiler to the folder. And so we can create multiple different cross-compiling targets. So, for example, you set your platform and your CPU, and you have some modules, and then you have these outputs for your target. So, for example, you can have an executable, and this should actually be a type unit test suite. Unit test. Okay, so for example, we have this unit test suite. So one of the things that we could do is we can create these unit test suites, and when we run them, it launches all of the unit tests that are defined in the code. So this is actually ran in a Docker container with native code. So I can, for example, go to this test module, and you can see, not that test module, so there's a module named tests, or target named tests. Here we go. So we have these like unit tests, and we have dual tests. So dual tests run inside the compiler, and they also run in the binary. So like if I take one of these unit tests or tests, let's say I change this. So let me run Q at the compiler real quick. So this is just the compiler itself that's going to run. You can see it produces a bunch of binaries. Right now it's kind of spammy on the output. I might change that. It's putting the hash of the output just so I could make sure it's producing the same output on different compilers. But I'm going to change this assert here. And what that should do is it's actually causing the compilation to fail, because this is a test that runs as both a unit test and a static test. The static test runs inside the compiler. So this essentially is constexpr, which allows you to do a lot of different things at compile time. And essentially, like C++ constexpr is kind of like static assert, but a little bit, static test is kind of like that, but a little bit more flexible, I think, in a lot of ways than constexpr is, because most things in the language are able to run in the compiler, with exceptions. For example, like you can't execute assembly and stuff like that, but most things can run inside the compiler. So if you have set, so by default it is going to run the tests unless you say static tests is false, I think. Oops, where is it? Yeah, so I think we can delete that, and it should probably fail to compile as well. I believe its default should be. Oh, maybe it's default off. Anyway, I'll probably change the default to on. But you can see it says which test failed. We can go to this test. We can see that. Oh, actually, that's just not implemented. Let me turn that back off. So we should still have that one failure. Okay, so this is the one that we want that we actually broke on purpose. Not all the code is implemented on all the targets, so some of them just don't compile. There we go. And it runs the tests with the compiler. So we get these executables that can both run tests with the compiler and also recreates that unit test that we can execute. And I have this script that launches the unit tests on the Docker container. So far, there's support for x64, ARM64. There is also support for Z architecture. I think theoretically there's support for RISC-V, but I don't have a RISC-V machine right now, so I can't test it yet. I'll figure that out later. I'm not sure if it works or not. So we can also execute, create binaries for Windows, and we can create binaries for Linux. But the standard library is not in the best state right now, as in there isn't really one. So for example, you will have to kind of write code like this, where I'm, creating my own system calls and things like that. And this memory allocator is probably not amazing. It has the ability to import procedures. So for example, you can add extern procedure and grab the virtual alloc call, and then you got to define the calling convention. So these are kind of like how I would bind things. I just say, here's my calling convention, and that's going to be in the order you declare them, but of course they're named arguments. And then this is the probably not amazing AI written memory allocator. We have templates. One of the serialization is kind of built in, so if you declare a struct, it is by default serializable as long as all the members are serializable. And we have some built-in keyword for some common formats that you might want to serialize objects in. Kind of like input iterator, output. We have some, so a lot of things are kind of looking like C++ here, at least that's the goal. So I kind of have this sort of string function here, and I have, kind of an allocator, because there's the default allocator that I'm using. And so allocation works at in the const expr. So if we go to the default allocator, if I can find it, we have the, wherever it is, the allocate function. And we have this sort of const expr alloc thing. So for example, it's using this runtime const expr statement. So it's saying, okay, if it's in const expr, it just grabs from the const expr allocator. Otherwise, it does like the actual allocation here by grabbing an address and then doing this begin alloc region thing, which is mostly for like address sanitizer or whatever. And it's kind of buggy at the moment, but it works well enough to run the tests. So we have different types of pointers. We have like the instance pointer, the array pointer. So like this is getting the address of the element at index 0. This is sort of the array pointer syntax. We have overloads working, procedure pointers, destructors, and we're doing this like three-way comparison thing. So you can return order less, order greater, order equal, and then it kind of synthesizes the other operations from that property, kind of like C++ three-way comparator. There's no support for partial ordering in the language. This is an intentional design choice that I don't want partially ordered types, including like floating points are fully ordered. So for example, if you want to do like, there's like IEEE equals, yeah. So, for example, if you have a nan, you're going to have to use this IEEE equals to get like the IEEE behavior because everything in the language is totally ordered. So that's just a design philosophy that I made, which is that every type is strongly ordered. And so if you want those sort of C++, C, Java, or any other language where the nans do funky things, use this like IEEE equals IEEE less and so on. There's a bunch of these functions for the sort of alternative behavior if you want that. I think array support is a little bit lacking at the moment. There is a lot of stuff that works with arrays, but some of the I would say they're not quite up to feature parity to C++ at the moment, with some of the array operations in terms of like built-in like functions and like standard array. But it's mostly good. Overloads for the most part just work. Let's see. We've got enums and flag sets, and so my sort of philosophy here is that there are a lot of times where people use enums when what they want is something that has flags and they OR them together. And so there's kind of a dedicated keyword for this called flag set. So for example, I have this open flags that should actually be, I think, in my PC flag set, but I don't remember. No, actually it doesn't need to. So we have this like concept of a flag set, which is where you have this sort of orable enum, and then the enum type itself doesn't really support like the OR operations. So right now enums are kind of like you just put them kind of like in an array, and then I am going to change the syntax a little bit. I'm probably gonna get rid of like reserved and stuff, and I may change how you like specify the values a little bit. But they have the comparisons, and then you can have you can kind of like just define a flag set if you don't need specific values. You could be like, here's my flag set, and these are the values that it has, and it'll kind of like automatically assign a bit index to each one that is going to allow them to be ORed together automatically. Let's see here, we've got some memory checks. This is not important. And then there's some tests here. I don't know why we test nanosleep. Some system calls, some glibc stuff. We have fusion types, which so there's 4 fusion types. There's a union and variant, and there's an inline version of each. So like an inline variant is like standard variant, and then the regular variant is like RPNX variant. So this is essentially inline. The data is it's a tag plus the enough space to hold the largest alternative, and then the non-inline version is basically a heap allocated version of that, which is kind of like the variant. And union is kind of the same thing, except it's named. So like each different option has a name associated with it. So for example, you could have like error as like a type, I think, like status code. So we have like status code, for example, which has options okay and option error as the possibilities, where it's got like reason, and these are like synthetic examples. where you have this function that returns a status code, and that status code is an error. And then you have this sort of match statement, case okay, and then you have case error as error. And yeah, you can mutate it, do whatever you want, and then run the match again, different cases. And then there's some like assertions and lifetimes. And we have this sort of concept of an antistatal, which is basically something that has a value that's determined before the program starts. And that's just like anything that is able to be constructed by the compiler before the program starts running, essentially. And yeah, so we have quite a lot of things to still work on. So coroutines are not implemented. Generics are not really implemented. We have templates, but generic support is not there. Now, interfaces are, which are kind of the precursor to generics. So we can have an interface, and then you can have implementations of the interface, which have different like overloads here. And then you can use those to like, it's like essentially like a vtable. So interfaces kind of provide the way to like implement vtables in a way. If you want to do that, you can use these interfaces. And then generics is going to be kind of the same thing, but also providing like a type erasure with heap-backed object storage that kind of makes the object, copyable or whatever. So you can store state along with the interface table. But those are not implemented yet, so we're missing coroutines. We're missing the generics, and we're also missing exception handling support at the moment. So those are the three like major, I would say, features that are not implemented. Oh, and there's also no inheritance or multiple inheritance, and then also privacy specifiers are not yet implemented. But we have like a lot of the other functionalities from C++ that we might want, like lambda functions are working. The syntax is a little different. So for example, this kind of syntax creates a lambda, so it's kind of this like dash less than, because it's like it looks like a lambda. I guess that was kind of my thought there. You just got to the return type and then just equals this sort of value, and then that's creates the lambda. Lambdas have a little bit different defaults compared to C++, so they are by default capturing all arguments by reference. So like this is capturing this x by reference, not by value. So that's just something to keep in mind, that there is a default capture by reference in a lambda function, or is it by decay type or something? I can't remember. And then we have this test here. Yeah. Oh, I should probably go over snapshots, because this ends like static eval. So one of the features of this is that we can take for example, parameter pack. The parameter pack syntax may change. This is not really set in stone. I'm not really happy with the way this works right now, and so I'm probably going to change some of this. But anyway, the important thing here is that we can create a static variable, which is a compile time variable, but we can mutate it at compile time. So we could say like static while I is less than pack size of b. We can say result equals blah blah blah. So this is like generated code, but then we can mutate the compile time variable, and then it regenerates the body of this expression after evaluating the static while. So this allows us to create variables that are evaluated and mutated at compile time rather than at runtime. So the static is like at compile time, but not just, it's not just we const expr assign a value, but we can actually do a while loop. So in C++, this would often look like, calling a template and then having another, like argument to the template where it just kind of calls itself with a different set of parameters. But we can kind of just do like a while loop in Quxlang instead, which I find a little bit easier to use now. C++26 is bringing in like a reflection interface, but I found the syntax really confusing. So I went with this instead because I thought this was a little bit easier to um, kind of get my hands on. But I did want a little bit more functionality as far as like unpacking like templated named arguments. So I'm not 100% certain I'm going to keep it exactly like this because I want to be able to like do something kind of similar to Python's like kwargs feature. So it may not work exactly like this in the actual first release. Um, but we do have that. Um, let's see here. Yeah. Yeah. So those would be, I guess, the main things. And there are various other changes. You have assembly procedures. I think I may have covered that in the last one. I don't remember. But we now have named argument support in these, so you can like call, like for example, Linux syscall write, no? Oh, syscall Linux. So like you see that we can do this with this like named argument syntax, and like you could change this. So for example, if I put the buffer over, oops, I don't know what just happened. I think I just control clicked something. So if I change the arguments there in the order, I can still run this and compile it, and even though the order has changed, I should get a executable that will still run correctly, and you can see that everything looks correct, like the right function still works properly. So you don't have to remember the order of the arguments anymore. You just kind of do the count. I may change this syntax. I may do like, I'm not 100% on this. I'm thinking maybe it'll be like buffer equals begin, fd equals fd, count equals like this. I'm not sure what syntax I'm going to use. I kind of like this one, but also this might be a little bit easier for people. So I'm not 100% sure what I'm going to do there. Maybe if you have feedback, let me know. So those are the I guess different options that I would work with. And I guess as these are for loops, I should probably go over the for loops. So for loops are not really finished, but there are various options. So you can say value from 0 until block count loop. For example, we have like test, we have init, test, step. So sort of this is the more C style for loop. You have value, and then there's a filter option. And then we also have labels. So we have like, so if you're familiar with JavaScript, like named, break, and continue, those are supported. So we could do like named, break, and continue. You can also break out of a label like this, kind of like in JavaScript, if you've ever used that. This is also supported, and it's also supported for the goto statements. And you can like use goto statements with labels. Oh, and also we have expect compilation failure, so you can test that something doesn't compile if you want to, or that something like crashes in the compile time, if you want to make sure that that is not possible. Oh, and also we have snapshots. So if you've seen these sort of static variables, Normally you can't refer to them at runtime, but if you do this sort of snapshot thing, you can. So it creates a snapshot of the static variable at that moment in time. This is just so that you think like, oh, I modified it, and then it has the value it had previously, just to make it clear that you're actually taking a kind of a snapshot of the static state of the variable at that particular moment in time, so that you can create a snapshot to that particular state that the static variable had. So in this case, it has a value of 0, and then we take a snapshot of its value, of a pointer to its vat, and then we get a pointer to that. So that's a pointer to I32. We evaluate it, and we can see that the value doesn't change, even though we did x plus plus here and x plus plus there, because we actually taking like a static snapshot of it at that moment in time. So you can kind of generate a table, take a snapshot of it, and then continue mutating it and do another snapshot and get another table. Something like that, for example. So if you want to do like mutations, you can. Yeah. Anything else? Yeah. So those are the main things. So we have quite a few unit tests that do run also on Windows. Mac OS is not yet supported. As far as a target, we can obviously compile on Mac OS because that's where I am right now. But it doesn't generate Mac OS binaries right now. So it can currently generate Linux binaries, and it can generate Windows binaries. We have tests for ARM, x64, and ZARC at the moment. Yep. Okay, so that's it for today's devlog. There is a Discord now, and I will post a link to that in the video description if you want to follow the language there. So you can put feedback or whatever if you want. All right, that's it.